this is my not first time in Hong Kong, not in China, but in Hong Kong it's my first time, and I'm delighted. So I'm going to present to you this subject, which is a mixture of three, if you want, worlds. As you will see, one comes from quantum and quantum information people. A different one comes, and also and especially people who do quantum matter. Then there is a line that comes from string theorists and black hole theoreticians. And I would submit to you that statistical mechanics has a lot to say on this subject. So, okay, so the original interest for these, do we have a pointer? No? Okay. Even an analogic, one. So the original interest here, oh, it doesn't move here. Oh. So, I don't know, I can change here, but. Oh. Let's see. Let's see. No. Thank you. Now I cannot change here. How do I change? Not nice. Sorry, how do I? You can do up and down. Oh, it works? Okay, okay. Thanks. So, okay, so the idea generally that I will discuss is the following. There is an idea that under certain circumstances where the system is very quantum, so at low temperatures and at biggish values of h bar, some systems have a time scale that is simply h bar divided by the temperature. Notice that everything else has gone from the system, and this is a time scale that only depends on temperature and a fundamental constant. You see, temperature, h bar has times of energy times time, and temperature has units of energy, so this is a time scale. And there is the idea that certain systems, including black holes, for example, and systems that are undergoing at very low temperature are very close to a quantum phase transition, depend only on this time scale. And you will see why this is interesting. When and under which conditions is something that is not clear, and I will show you a bit the panorama we have today, and what are the consequences of this. So this is an interesting physical question that people who were more related to field theory had in mind, because it's something that you expect of black holes, but as you will see, it has consequences for everybody. So one of the consequences, and where all this story started, was with transport. So two examples of transport is when, for example, conductivity, you put a minus sign here, a plus here, and the electrons travel towards the right. This one you know. And the goodness of this sample as a transporter is, of course, the conductivity, the electrical conductivity. Another case of transport that sometimes it's not expressed in these terms is the transport of transverse momentum. So you inject transverse momentum on this side, and you take it away on this side, and particles will have an excess of momentum in that direction here, and will lose it here. And this is just a very complicated way of saying that you're shearing your sample. The conductivity of shear is the viscosity. How well the sample transports shear is the viscosity. Notice that there is something slightly anti-intuitive. it is a better conductor of shear if it's a solid or if it's very viscous. And if it's not viscous at all, you want to apply shear here, but the transverse momentum doesn't propagate well to the other side. This might be a bit anti-intuitive because one tends to think of high shear as bad conductor, but not. It's a good conductor of transverse momentum. Okay, and then the idea came, and I can tell you a little bit from where, that, well, first of all, a fastest time scale, as I will show you, implies a bound, and that there was a bound, a lower bound, for all these conductivity processes. So these people, Cocteau, Stadinets, and then other people, began with a model, which is a model of field theory, of string theory, and did things, and then they conjectured that they obtained a value, and they conjectured that this value is the limit, the lower limit that something can take. So everything else is going to be higher conductivity, higher viscosity. So this was a conjecture. They said, okay, we get this for some model, and then we conjecture, because of what we think the universe is made of, that this is the best you can do. And then there is a nice review of Hartnell and Mackenzie. Sorry, Mr. Mackenzie, I didn't put him, where these things are discussed. So let me tell you how this works. By the way, I'll spoil you now. These bounds on this transpose coefficient have not been proven, and the situation is very unclear at the moment. So there are apparent counterexamples to the original guess. It is still not clear. Okay, so how does this work? Well, imagine you have, these are little spheres, hard spheres, and I stuck some on the boundary so that I can shear the system. And we are purely classical at a positive temperature, so the particles are banging around. And now you shear this, and of course you transmit a bit of an extra speed in this direction here. And as they collide against the other particles, they transmit their extra momentum. And then and these one transmit the extra momentum in the other direction. And in this way, the system transmits transverse momentum and has a shear viscosity. Okay. Now take this classical system to 0 temperature. Now they are not moving, and now very slowly, remember I am in a linear regime, very slowly I shear it, and the particles simply do not go to the next particle to tell the next particle, listen, you want to move a bit more in that direction. So the shear viscosity, when you calculate it like this, drops down to 0. Simply because particles don't move, so they cannot get to the next neighbor and tell them, here is my extra. But now let me consider the same situation, but now I turn H bar on. And now something different happens, because the particles, being quantum, they do not like to be too much together. Quantum systems, like putting a particle in a narrow box, do not want, and you pay this with an extra energy. If you want to squeeze a wave function into a narrow channel, you will pay this with a higher energy. You know that when you have a square well and you make it narrower, the levels become more separate. So what happens is that even at 0 temperature, these particles are talking to one another because of this quantum phenomenon. And you get that you can get a viscosity for lowish temperatures that is much higher. So this gives you an intuitive idea of why there should be a lower bound for shear viscosity. And the bound that was conjectured that I mentioned before is that if you take the viscosity and you normalize by the entropy per unit volume, this should be bigger than this number. Notice that this is completely model independent. It only depends on H bar. So this was the original conjecture. And, well, we are very far away from proving anything for a system like this one. But as I said, it was done for some string model and conjecture that this was the best you can do and everything else would be larger, and this is the conjecture. Okay? And notice how model independent it is. Why should we care about this? So two reasons. If the system all systems at given temperature have a lower viscosity that is allowed, then get things that want to be not very viscous, that you know for physical reasons that they are not very viscous. Get 5 different materials that are not very viscous. They are going to crowd, if there is a bound, they cannot go all the way down to 0, and the best they can do is to go towards the bound. So, in fact, it is true that when you look at this bound here, which is called the Planckian bound, in fact, many substances have a viscosity that is not very far from that value. And you could ask, how can this be? Very many systems, or quite a few, have a viscosity that is close to that value. If you have no bound, you wonder, is this a universal thing? And the explanation, if there is a bound, is very easy. They want to have if I do a plot of viscosity, there is a bound here, let's say, and the best they can do is to take values. No, it's okay. I'll deal with it. Don't worry. The best they can do is to be. So from the point of view of real quantum matter or real matter, so from the point of view of matter, it is an interesting question. And this is, you can find, now I put the 2 names, this in this review. This is the interest for, let's say, ordinary physics. For string theorists, there is an added thing, which is, as I said, that the black holes, they conjecture or they postulate that they are, for reasons that I don't know why, they should be the fastest objects in the universe. And so having a bound and reaching it is a symptom that black hole physics is around in their eyes. Okay? So for them, it is interesting as a diagnostic of having the things that are associated with black hole, holography, and so on, which I will come to in a second. Okay, but nobody has been able to prove for the moment anything like a bound, like this bound. So, but there is another quantity which you can use to study systems, which is the Lyapunov exponent. So is a measure of chaos. So let me tell you what a Lyapunov exponent is in a classical system. The best way to understand it is through an experiment that is called Loschmidt-Echo. You run the system, measure an observable A, run the system, and then if you run it with the time reversed, you will come back from when you started. Okay? So now you do something slightly different. You run the system, give it a kick with another observable, a small kick, and then you return to a slightly different place. The measure of chaos is, given a kick, how distant is the point where you return to. Okay? The system is if the system is very sensitive to initial conditions, when I evolve it like this, and I kick it a bit, instead of coming back here, if it's sensitive, it will come back very far. And the measure of this, it's an exponential thing, and the measure is called the Lyapunov exponent. So mathematically, this you can put it this way. You want to measure how much this changes when you change a little bit this, and you can do it in several ways, but it is the Poisson bracket between what the observable is at time t and a given kick in B. This is kind of a response function. And this, if you have a chaotic system, goes exponentially with time, meaning that the same experiment, if I do it with longer times, because it has more time to separate, they separate exponentially, and this distance is given by this quantity, and it's exponential in time. This exponent is by definition the Lyapunov exponent. It measures how much two trajectories that are slightly different separate after some time in a chaotic system. When the system is chaotic, you have a positive Lyapunov exponent. If you have zero, then it might be not chaotic. Please stop me with questions as we go on. Don't wait to the end. Okay. The problem, why do I prefer this experiment rather than saying two nearby trajectories, is because if I want to go quantum, the notion of trajectory is simply not there. So what do? Well, these gentlemen, Larkin and Ovshinnikov, thought away. They said, okay, if I write this thing as a Poisson bracket, this Loschmidt-Teko experiment, I can perfectly well do a Loschmidt-Teko that is quantum, and I can ask myself what it gives. And not surprisingly, it gives the same thing. This is a measure on the Gibbs measure. And this quantity is a commutator, but we know from our quantum mechanics courses that a commutator is the natural quantum version of what a Poisson bracket was. So it's all very well. So here you can define a quantity that is quantum. And if this one grows exponentially, then you will call this a quantum Lyapunov exponent of a quantum system. Okay? Notice that the Lyapunov exponent has units of inverse time, because this is multiplied by time. And it just tells you how much a system diverges, how chaotic it is. Okay, this is a 4-point function, as you can see, because I have A of t times b squared. So A of b times t, A of b times t. So there are 4 operators. Okay. So in quantum mechanics, this is written, the transformed one. You see here, A to the I t over h, A to the minus, is the evolution operator of A in the Heisenberg. E to the I delta E to the is the kick, and E to the minus is the coming back. So this, what I wrote here, is just this written in normal evolution. Okay, and then very much on the spirit of what I was talking before, Maldacena, Schenker, and Stanford proposed that the Lyapunov exponent has to be smaller or equal than this number. So first of all, I told you that the Lyapunov exponent has an inverse of time dimension. And here, what is the time? This is the Planckian time, h bar over t. So this universal number, which is the Planckian time, is the inverse of that is the greatest Lyapunov exponent that you can have. But they found the 2 pi, but it is already quite interesting, the fact that this scales like a Planckian time. There is no detail of the system whatsoever. So this is kind of in the same spirit of the bounds we were talking before, bounds on the typical time scales. Now, as you will see, you can find that the Lyapunov exponent is less interesting than a transport coefficient. Transport coefficient is something of the physics of the system. The Lyapunov exponent is more or less not very useful. And if you do things like that, I would say I agree. But the advantage of this Lyapunov exponent is that for him, we can prove a bound. And it's the only one we have for the moment. So this bound, and we would like, everybody would like, to be able to write something like this for viscosity, for conductivity, and so on. Okay. How? Yes. I will give you the closest to what you are asking in a couple of slides. The closest I know to what you're asking. So a simple explanation that you can almost explain to your hairdresser. So in spite, okay. The proof instead that these people made is not super difficult. but it's something about um, analytic functions in the complex plane of time and temperature in this case. It's as so we will talk later of a simpler proof which contains perhaps the same elements, but it's more physically attached to things we already know. Okay, an important side remark for those of you who do quantum, there is a model which is called Sash-Devier, and Kitaev added something, which is a model very much like the ones Laetitia was discussing, but these guys are fermions. Forget, but this model happens to saturate this bound. So remember what I told you. If something saturates the bound, this is taken to be an indication that it is a decent model for black holes. This is philosophy, but this is how this model gained its nobility titles and became studied by thousands of papers, because it went all the way up to a bound that is what people expect from black holes and pretty much nothing else. So this is half sociology, half physics, but it's good to bear in mind, because it tells you something about what these bounds are for. Okay, so notice that a new actor appears in our world, which is when we go quantum and we substitute the Poisson bracket by a commutator, we develop the commutator A times B minus B times A squared. And you can convince yourself that the only term that is interesting is this one. Of the many other terms that are here, the only one that matters is here. And this is the now famous OTOC, out of time order correlator, because you see you get an A of t, and then instead of going to higher times, you decide to go again to B of the original time and again to A of time. This operator entered through the window, through this commutator, and has become the object of, again, thousands of papers in the last years. Okay, and let me tell you very quickly, because we will need it. You see, this is the commutator I wrote here. You can write it in very much similar ways, but look at this one. I have split the Gibbs measure in four. Two I put here and then I square, and I here split it in another way. You see that they are basically the same thing, but instead of the Gibbs measure putting it at one extreme, I am cutting it in little pieces. This is part of the game. Don't take it so seriously. It's just almost a choice, but it will be important for us in a second because it is important for the proofs and so on. Okay, but this quantity has the Lyapunov inside. That's the point. Okay, now I'm going to do what Leihan wants me to do. Let's try to do an analysis to try to understand why should quantum mechanics limit chaos? Can I understand this in simple words? If I can, it will be a great thing, because all this comes to us from what string theorists do, but there is a question that we have in the back of our minds. Okay, once you've talked about black holes and all the such, is this just the uncertainty in principle in some sort of new vest, or is it not? And I will try to convince you that it is, that an ordinary physicist, a humble physicist can get to this. Okay, so let's try to understand. It's a thing that will happen at low temperatures. So imagine I have a particle in a potential, or many particles in phase space, it's the same thing, and I go to very low temperatures. I know what happens. The wave function tends to localize at the bottom of the well, and to a first approximation in the semi-classical analysis at low temperatures, you have oscillations down here. So with low temperatures this way, we are not going to get chaos. So if I want to get chaos, it seems, and so the bound will be satisfied, but that's not going to be great news because you don't have chaos. Who can be chaotic at low temperatures? Well, if the ground state is, on the contrary, degenerate on some surface of higher dimension than 2, then the system, even when it is at the bottom, can still play around. So if I want to put the bound to test, I better do something like this, because here the bound will be respected, but that's not going to be good news. That's not going to be new. Okay, so let me try this variant. So I'm going to do a potential whose bottom is a certain manifold that is flat in energy. But then you say, okay, but this is, if I have a flat bottom, why not simply study the bottom? Like when I have a quantum wire or a sheet of metal, the potential constrains you to be on the sheet, but then perhaps you don't want to study the three-dimensional space. Perhaps you just want to study the curved space where you can move. So what I'm going to do is exactly that. I will eliminate all this and just say, oh, I'm restricted to moving below, just for simplicity. This contains essentially all the physics at very low temperature. Okay, just in the same way that a potential that confines me to a wire makes my system one-dimensional, for example. Okay, and so how do I write this? Well, in general, on a surface, the Hamiltonian, if you're moving freely on a surface, is going to be something like this, p squared essentially, but there's going to be a tensor, which is the metric tensor, which defines the local curvature of the sphere, the geometry. All the geometry is written here. And this will live in a number of dimensions, and it could be chaotic very well. And we have lost all that is inessential, and we are at very, very low temperatures. Our only energy is now kinetic on this surface. Are you good with this? Okay, so now let's move on this surface. The surface has something that reminds a lot of the Lyapunov, but is pure geometry. First of all, particles on a surface move along geodesics. Geodesics are minimal length between points. Second, two geodesics can separate exponentially as I move along them. And this is called the geodesic separation. And it tells you that as you move along here, a nearby geodesic separates exponentially with the distance. This is what happens with gravity. It's a thing that people who do gravity study, because two rays of light precisely separate in this way in a curved universe. And okay, and of course, the geodesics, you are running on them at this speed, basically, which is the kinetic energy. Remember, that's the only thing you have. Okay? So the speed, obviously, is the moment divided by the mass. And so you have two elements. You have the geodesics, which have their natural separation, which you draw them on the surface and you're done. And of course, you can calculate them only on the basis of the G tensor, because that's the only thing there is. And along them, you move with this speed. Okay, so now let's say the separation between two geodesics, I said, was exponential. So it's e to the L is how much I move along them, divided by, I don't know, you see it here, it's an L0. L0 is the typical scale at which the separation goes from 1 to E, conventional typical scale of an exponential. Okay, and now we do the calculation. So L0 is a property of the system. It's the typical distance at which two geodesics separate. This depends on how bumpy your thing is. So, okay, so the Lyapunov exponent is going to be this separation in space times the speed at which you move along them. No, just dimensionally, you can see, because I'm going to separate from my neighboring geodesic, but at a rate which depends on how quickly we both walk. So it's this times the speed. Mass, let's put it to 1, so it's P divided by L0. Now I do a little trick. Okay, I want to move, yeah. So now I do a little trick. Instead of, okay, I multiply, what did I do? Oh, sorry, there's no equal here. So now I want to do the Lyapunov times h bar divided by t to see if I get the bound. And so I put this in here, sorry, this step, you can forget it. But if I put here H bar, sorry, so I get, if you see like this, it's okay. So you got Lyapunov equals to P divided by L0. But remember that the thing that is the bound is H bar times the Lyapunov divided by T. So I have to multiply this side by H bar divided by T and see what I get. Sorry, there's a typo here. And so, well, when you do this, and now the other thing I have to say is that P is a square root of the temperature, nothing special there. And when you get to the last step, what you get? What do you get? This is a one-liner. You get that the Lyapunov, sorry, not the Lyapunov, the bound, which is the one that has to be compared to 2 pi. What you're doing is comparing the de Broglie length, the typical wavelength with the typical length at which two geodesics separate. And this is more or less what you were asking for, no? An explanation that anybody can understand and digest. The argument would be, you cannot separate faster than a wavelength, typically, which to me sounds supernatural. And as you see, it tells you something very interesting. It tells you that whatever the origin of these inequalities, the essence of them is nothing but the good old uncertainties of quantum mechanics. Okay? So this is something nice. And so what happens is, if you do the de Broglie length is proportional to the square root of the temperature. This is, and so as you plot this 1 over the square root, which is something that you obtain by tuning down the temperature or tuning up H bar, and you write what is the quantity that normalized. So this quantity goes up as you go down in temperature. It goes up because there is a beta is 1 over the temperature until it hits what would be the bound. So a semi-classical calculation gives you this, and then here something has to happen that tells you, sorry, but I don't want to continue the semi-classical approximation to lower temperatures because I'm going to violate the bound. And this happens at precisely the moment that I mentioned before, where the temperature is so low that the de Broglie length becomes comparable to the geodesic separation distance. For example, between hard particles, superfluidity appears at that temperature, which is sort of nice. Okay, so we have been playing because, okay, now you say, fine, but okay, but how does, in detail, how does H bar stops me from being chaotic? So we tried a system that is the most famous system that has a Lyapunov exponent, a curved surface, which is the curved surface of negative curvature, which you can project down, and it becomes, these are the geodesics on the Poincaré disk. So the geodesics on this can be projected down to a disk, which was introduced by Poincaré, and it gives you a geometry, which you can also quantize. So it's a nice place to try to understand how is quantum mechanics stopping you from being chaotic. So, well, you plot the separation or the OTOC or whatever, and you see that it has a Lyapunov regime, as it should, with a gradient with exponent that it has to have, which is given by the curvature of this surface. Okay, so to understand this, what we did, okay, quantum mechanics doesn't want me to violate a bound. So it doesn't want me to have such a big Lyapunov exponent. So what we did is the following. We studied, first of all, some kind of tube, which is, this has no curvature. This is simply a cylinder. The Lyapunov exponent is 0 here, so this doesn't contribute to chaos. Here we will put a lid. We will let a particle move on this, and then it will enter a region where it has the curvature. So a classical particle moving here would move nicely without doing anything here. Here it will have all the chaos, then bounce back, and then bounce back, and then up and down. And for the classical particle, all the Lyapunov comes from the time you spend in the blue region. So the particle goes boing, boing, but in that region, it begins to feel chaos, then it comes back, it doesn't feel chaos, but then it comes back and it does, and so on. What happens with quantum mechanics? Okay, this problem you can solve exactly in quantum mechanics, and it's easy to solve. And what you find is that the wave function at high energy comes, gets into the blue region, bounces back, and nothing special happens. This is at high energies, for example, high temperatures. But as you go down to low temperatures, what happens is that the particle has a wave here, but when it reaches these curved regions, the curvature makes kind of an effective force, and this is an evanescent wave, as if it had a step in a potential. You can do the calculation, it's very easy. You go to cylindrical coordinates, and the curvature gives you an extra term, which acts as a potential that makes you bounce. So a quantum particle doesn't like to be there because it's quantum, because curvature repels it, sort of. And so what you get is that this is not contributing a lot to the quantum Lyapunov because this thing is not letting it do much inside the region. So when you want to enter a region that is very curved, quantum mechanics tells you, I don't like it. Go back. And so you spend less time there, and this is how essentially here at very quantum systems, you're mostly on the non-chaotic part. We have played with systems that have two levels just to be able to. So a lid, a cylinder, then a part with a certain curvature, and then a part with much more curvature. So when the wave is very much like this, it goes all the way to here, and you have the Lyapunov that you have classically. When the wave is a little bit longer, here you're okay, but here you don't want to go in, and you just like the phenomenon we saw before. And when the wave is even longer, it doesn't even want to be in this part, which has a smaller curvature. So it bounces already here. So this is how bigger and bigger curvatures begin to act. This one at the beginning, this one in a more quantum system, and so on. This is just to have an idea, and this is exactly what you see. A high energy, you have three stages. This is a problem like this one. Intermediate regime, you see the wavelength is longer, doesn't want to go into the very curved region, and a still longer wavelength doesn't want to go in the two of them. So the Lyapunov will be the classical one up to here, but this involves a smaller curvature, so it's medium. And here you get nothing, basically, as you go down in temperature or up in H bar. Okay, so this gives you a feeling of what goes on. And just how much time do I have left? 15 minutes, no? 10 to? Or 10 minutes more. Okay, it's good. So if you like this kind of systems, there are higher dimensional systems of this kind. This is particles, hard particles in a box, but you can also see it as a billiard in 3n dimensions. The inequalities that the particles have to satisfy as not to overlap can be seen as sides of a polytope, and you're inside. So this one you can analyze with exactly the same way. The motion is free inside, and then you just crash against the bound. There is a nicer one that was done by Batarji, Shubro Batarji, and Roderick Mössner, which is these are spins, three-dimensional spins, living on this hexagon lattice, honeycomb, no, this is Kagome lattice, and in such a way that the sum of the spins along within each plaquette are zero. Otherwise, the system is free. So you see that there is interaction because these two spins participate in this sum and also in this sum. There is one per plaquette. And otherwise, the system is free. So you see that this is a manifold in, I don't know, 3n minus I don't know what, the number of constraint dimensions. So you can analyze this one in the same way. And this is what they did. They did it only the semi-classical thing. So they verified that Lyapunov goes like 1 over square root of t, which is the classical result. Unfortunately, we don't have yet what happens here. We know that there is a bound here, but who is enforcing, how is quantum mechanics, when you quantize this model, going to avoid you from going up? We still don't know. I have a vague intuition, which is that certain defects that happen in this lattice are blocked by quantum mechanics. But this is something that it would be very nice to do and very easy to do, because you don't need to do a big plaquette. If you just do 3 of these, you're already chaotic, and the mechanism should be clear there. So by quantizing, I don't know, 20 degrees of freedom, you're done. And well, nobody has done it, but it would be beautiful, because it would tell you, what is it of this spin liquid that is forbidden by quantum mechanics that makes chaos stop? And that would be a nice thing to do. Okay. This one I think I'm going to jump. And what about the proof? I told you that the proof of Maldacena, Schenker, and Stanford is a bit it doesn't speak to you a lot. So we did, together with Laura Foini and Silvia Papalardi, we made an easier proof, and then we discovered that a Japanese group of, where are they? Ueda, Shitara, and Tsuji had done a part of it. And the idea is basically the same. And it's based on the fluctuation-dissipation theorem, which is something we all love. The classical fluctuation-dissipation theorem, as you know, relates a correlation with a response. And it tells you that the response is 1 over t times something of the correlation. The quantum one is not so different. It tells you that the correlation, which is anti-commutator, and the response, which you can convince yourself is the commutator, they are related in Fourier variables in this way. So this is the quantum version of this. And the temperature enters. Okay. So what does the fluctuation dissipation mean? Because it's not just, oh, what a nice little equality that allows me to calculate half of the things. It has a very important and crucial effect. You can do this calculation. You connect a thermometer to many copies of your system, any system. This could be a glass of water, but you replicate it many times just to make the calculation simple. And you couple the thermometer to the same observable of all these systems. You want this thermometer to measure the temperature that these guys have. In other words, you want the thermometer to capture and be himself at the same temperature as these guys are. No, to tell you the temperature. The thermometer is not telling you what temperature the system has, it's telling you the temperature that it has. So how can we guarantee that this one will couple to those and will have the same temperature? You know it from thermodynamics, but if you want to do it dynamically, what you do is you couple it and you see that these systems are giving you energy through the noise, the system, the thermodynamic noise, and this thermometer is losing its energy through friction. The balance of these two things is what guarantees that this thermometer is at the same temperature as this, and the balance is given by the balance between correlation and response of the thermometer and of the system, and this is the fluctuation dissipation theorem. You may recognize that this is exactly the same argument of Einstein for Brownian motion. The particle of pollen receives energy from the crashes of the molecules and vibrates. It gives it to the same molecules through friction, and the balance between these two cannot be anything because the particle of pollen has to has to have the same kinetic energy as the water because it's in equilibrium, and this is guaranteed by fluctuation dissipation. All this is a speech in favor of the fluctuation dissipation theorem. Okay, so now remember that I told you that these could be right in three versions, which we expect to give more or less the same thing. Well, the proof that you can do that is equivalent to the one of Maldacena, Schenker, and Stanford is you apply the fluctuation dissipation theorem one-to-one, and you discover that these two are related by fluctuation dissipation. You see that they are positive because this is a square and this is a commutator squared. Okay, so when you apply the fluctuation dissipation theorem here, and you suppose that the things are going exponentially as you expect, what you discover is that you get a factor which measures this. The fluctuation dissipation theorem tells you this. And the way that two positive quantities that have this proportionality constant can be both positive is that this cosine is positive. And this gives you the bound. Don't bother about the details. You can go to our paper with, which is a bit more complicated. But the fact is that, again, the version of the theorem, which you're a bit doing things that you don't know exactly what they mean, you can convince yourself that even the proof has a simple explanation, and it's based on the fluctuation dissipation theorem. The original proof is based on an analytic continuation. The fluctuation dissipation theorem too. So what did I gain? Well, what you gained is that the analytic continuations in life can fail, but the fluctuation dissipation theorem cannot, because if not, all thermodynamics collapses. So we are pretty sure that this is a rock solid basis to start things. Okay, what about transport coefficients? This was for the Lyapunov. We still do not know. We are hoping to be able to contribute something to this, but I would say that people are pretty much stuck in the sense that for transport, they haven't had the success that Maldacena, Schenker, and Stanford had. It's not even clear if the question is well posed. So is there a bound? But when? Maybe the hypotheses are not well chosen. It's not something where you have the hypothesis, and if you're clever enough, you will do it. It's probably not true in general. So what is the good question to ask is not clear. Is there a bound in some cases? One has a gut feeling that yes, but for the moment, we don't have that. And that would be for a physicist much more interesting than a Lyapunov exponent, no doubt. So at this point, I thank you very much for your attention.
But I only have very superficial understanding of this material you presented. But I think last fall there was a meeting, Nobel Symposium in Cape Town, and this cosmologist Neil Turlock. So he presented a very interesting kind of observation on complexity. So he take the square root of the geometric mean of the Planck length with the size of the universe and come up with a length scale which is maybe 10 times the size of a cell. So what he says, things become very simple when you go down to very small scales or go to very large scales, and the life happens, on a scale of maybe 10 or 100 times the size of a cell. So do you think at some point one can come up with an explanation that the most complex behavior happen on the scale that we see in nature?
I don't know.
But the square root, is there any reason for this geometric mean?
No, I don't know. I don't know. it would be interesting to know, maybe Herb knows, a simple argument for the size of a cell, roughly, because they're very different.
Yeah. Because they try to
I'm very far.
You pack information structure, into living, cells, organisms. Is there a fundamental limit how much complexity you can put in for a given size? Yeah, but they are different in complexity also. I mean, probably they have not reached that fundamental limit, but is there such a limit? But supposedly, if you have a cell that you can put in more computing power, these different organelles that can make it run more efficiently, that has some evolutionary advantage, possibly. But have we reached some kind of a limit? Anyway, it's a wild question.
No, that I definitely don't know. No, what I think is very nice is to discover that questions that had the aura of incomprehensibility that is typical of very high energies, many times are just elementary physics applied, as you saw here. This for me is an enormous pleasure to discover and to see. But other than that, I have no other deep message to give.
Just some also wild questions. I'm not quite familiar with what you talk about, but very intriguing that to see the fluctuation-dissipation theorem put a bound on the quantum chaos. Does this also happen for classical regime? From my knowledge, it seems that fluctuation-dissipation theorem doesn't relate to the Lyapunov exponent in the classical regime, but how does it relate to the in the quantum regime?
Because one thing that we learned in this business is, I closed my computer, but let me write it. So the quantum fluctuation dissipation thing reads something like the imaginary part of the response is related to the hyperbolic tangent. I think this is something like this. Okay, and typically when you want to go classical, you linearize these because you say that h bar is very small or whatever. Now, you see that this already has a Planckian scale inside. This is the Planckian time scale. So it means that fluctuation dissipation contains something where this tangent, which has some information on the quantum thing, and this function is essentially linear in the semi-classical limit. It sort of levels off at a typical omega, which is the inverse of the Planckian scale. That is something that is in the literature, of course, in Scubo, I don't know. But and we try to do this in the paper, when you take these formulas and you take them to the time domain instead of, they get more complicated, but you realize that this passage here is a convolution with respect to a time scale, a sort of window that contains a time scale. So fluctuation dissipation acts as a kind of blurring of all functions at that scale. So it contains something quantum that is very interesting and that is not often, as far as I know, said. So our feeling has been, okay, if we had to work on trying to say something about quantum bounds other than Lyapunov, our prejudice is that we will be armed with a fluctuation dissipation relation in our hands and see where does this take us. But given that we haven't been successful for the moment, the jury is still out.
Thank you.
Hello. You mentioned that you consider a system where the energy is flat and you confine it in the plane that have equal energy, and the geodesic on the plane is getting separated very quickly. Is the separation can the separation be arbitrarily big?
The separation, if you are
like quick,
yeah, the geometry in, at least if the surface is a normal surface that you put by hand, you can do it as big as you want.
So
the surface is itself dynamical in some way, maybe not. Maybe H bar will play a role, and this is maybe interesting what you're saying.
Right.
Because then you would say that you don't want curvatures that are very big, very sharp, because somehow quantum mechanics doesn't allow you, if the surface has some dynamics to it. And then it might be interesting, yes. But the way we're doing it, no, because the surface, we give it once as we like.
Oh, okay. So if it is growing very fast, then how will a particle move on this surface?
So the wave should scatter. Now, one tends to feel that, and this is just a hand-waving argument, that a wave that has a given wavelength, you wouldn't like it to scatter too much on scales that are much shorter than that. This could be kind of a Rayleigh scattering, you know, but in any case, it seems that it's remarkable that in doing the calculation this way, the comparison that naturally appears is between your wavelength and this separation that is a property of the system.
Okay, I see.